Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Bueno, ahora viene la ponencia del doctor Héctor García Molina, que muchos de ustedes lo conocen. El doctor García Molina es profesor del Departamento de Ciencias de la Computación y de Ingeniería Eléctrica de la Universidad de Stanford. Así que les pido también que demos la bienvenida a Héctor con un fuerte aplauso.
So I'm going to be speaking in English since that's what was been requested. Let me just say a couple of words in Spanish. Me disculpan por hablar en inglés, pero creo que es mejor para los que no hablan español que hablen inglés. Si quieren hablar conmigo en español, encantado después de la plática. So I'll switch back to English. And it's a great honor and a pleasure to be here. I always appreciate Microsoft's invitation to participate in these events. It's been wonderful, great location. Everything is fine. So I'm going to talk a little bit about some of the research that we're doing in our InfoLab, in our group at Stanford. And the topic is crowdsourcing. So I understand that Peter already said a few words about crowdsourcing. I had to step out for a minute while he was giving his talk. But just briefly, crowdsourcing refers to using common people out there to help solve problems that computers have a harder time solving. And it's definitely not a new idea. Back in the Wild West, the sheriffs were using crowdsourcing. They were asking people out there to help out with a task. They had a reward when the task was completed. So it's an old idea that's been around, but it's become very popular these days because of computer networks and the number of people that are using computers. So there are two common terms that you might hear. There are two related terms. One is wisdom of the crowds, which also is related to the crowd, but has to do more with taking what the crowd is already doing, like typing in queries into Bing, for example, and analyzing them to learn what the intentions, what the thoughts of people are. But I'm going to be talking more about actually going out and asking people to participate in an activity for pay, for instance. Another term that I put more as a joke there is cloud computing. The similarity between crowdsourcing and cloud computing is that they're both buzzwords and they're both rather vague, and basically whatever you're doing these days can be put under crowdsourcing or cloud computing in a sense, but don't confuse the terms for my talk. Okay, so I understand that Peter also had a little experiment this morning for you, and I'm going to have, since we have a crowd here, this is ideal for crowdsourcing. And it's also very similar to what Peter said. It's dots. It's actually a test that we're using in our research, so that's why I selected it. But there's a key difference. Peter didn't get anybody to answer his question, I understand. But he forgot one important aspect, which is rewarding the people that participate, having incentives. So Ophelia here has volunteered, and I have some cash here that we're actually going to pay people. So why don't you take the bag? And I want Ophelia to help me find 5 or 7 volunteers, maybe some of the students who need money more. And you're going to be paid 5 cents, a nickel, so each one. So give them out to 5 or 7 people. Raise your hand if you want to participate in this experiment. Yeah, don't forget that you're getting the money, right? So don't take the money and then don't do the work, which already is a problem that you see with crowdsourcing, right? How do we get people to do the real work and not just take the money? We have some volunteers over here. So while you're getting the money, and this is typically there's sites like Mechanical Turk, for example, where you go and you get small tasks and you get paid 2-3 cents. In my case, I'm offering 5 cents for this particular task. And you can do many tasks, and there are actually people all over the world that are making a living working on tasks that are generated in this fashion. Okay, so do we have 5 or 7 people? Yeah, that's fine. It doesn't have to be exact. Okay. Now, I'm not checking if you have. I know there's a lot of non-Mexicans here. Maybe I'm supposed to check if they have the right work visa for this. I don't know if I'm going to get into trouble for this or not. But anyway, raise your hand if you're working. Okay, so how many? Hey, wait a second, we have only 3? Oh, 4. Okay, good, okay. So I'm going to show you a number of dots, and you're going to have a limited amount of time. Why am I limiting the time, Bill? Because people that work on crowdsourcing do tasks relatively fast because they want to do more tasks, so I'm simulating that environment. So you'll see a number of dots, and you have to tell me if there are more than 45 dots or fewer than 45 dots. Why is that an interesting question? Well, perhaps you are a mall, a shopping mall, and you want to find out what are the peak times in number of people, so you're showing people photographs of the mall, and people are supposed to count how many customers are in the mall at that time. So these are not photographs, these are dots, but it's sort of the same idea. There are cases where people can analyze an image faster and better than the computer, and that's what you're doing here for us. Okay, so here's the question. So take a look at it, the people that are working for us. Okay, so of the people that are paid the 5 cents, raise your hand if you think there were more than 45 dots. Okay, we have 1, 2, 3, 4 dots. And now how many people think there were, what did you say? Those were the less than 45? Oh, more than 45, 4. And less than 45? 45. Or 45, well, less than, there you go. So we have 2, okay? So you're beginning to see what the issue is. The crowd is not perfect, right? People have different opinions. Sometimes it's a subjective question, sometimes it's not, like here. But because of the rush or the difficulty of the question, you might not have the right answer. So one of the things you have to start doing in crowdsourcing is asking multiple people. And the question now is, what do we do? Do I take the majority or the average? How do I combine the answers of people? Now, there might be some people that are just lazy out there, or spammers as they're called, that are just doing this to cheat me out of my 5 cents. How do I detect people? Do I look at their pattern, how they're operating? Do I look at the response time? If they're answering too quickly, maybe I should not take into account their answers, or I should weigh them less than the other answers. The people that disagreed, the 2 or 3 that disagreed with the majority, maybe I should fire you, and you shouldn't work anymore for me. Or maybe I should give you 3 chances, and if in those chances you still disagree with the majority, then I can fire you. All of these questions are things that people are looking at in this wide area of crowdsourcing. So I have another question just to see if we still get disagreement. So the same question, but now a different set of dots. Ophelia, can you hire 5 more workers for me, please? Yes. Oh, he wants to work too.
He wants to work?
No, the guy with the microphone. No, I'm just kidding.
No. Enrique works. Okay. Someone else? You too? Okay.
And Ophelia, you get to get the change. Whatever's left over is for you.
Okay. If they don't work correctly, someone else? You? Okay.
Okay.
And, ladies?
So this is
Please. Another
quite
one?
a nice pay. 5 cents. You can do a lot with 5 cents.
Someone else? Dollars. Eh?
Yeah,
Okay.
no
Okay.
less. Okay, so
That's it.
ready? Okay, thank you, Ophelia. You've done a great job as my assistant.
Thank you.
Okay, so here you go. More than 45 dots. Take a look. Okay, so how many people said there were more than 45? Oh, well, I guess people that are not paid are also voting, or did we give out this many coins? Anyway, how many people said less than 45? There are fewer. Okay, 3. So maybe we should believe the majority, right? I would guess. But in these tests, you never know. I mean, if the computer doesn't generally know what the answer is, we have to rely on the crowd. So that's the type of questions we want to address in crowdsourcing. Okay, so there's a lot of interest in crowdsourcing these days. Here are the names of some of the companies that we know of that are in the crowdsourcing space. There are lots, and probably we missed a whole bunch of them. So there are lots of small startups, slightly larger startups. They do all type of work. I mentioned Mechanical Turk, which is part of Amazon, where they do micro tasks, little tasks for pennies at a time. There's companies like Odesk, where it's bigger tasks. You actually hire somebody to write a program for you or to write an essay, for instance. There are companies that go to the crowd out there. They don't know who they're hiring. There are companies that actually hire people in the Philippines. For example, they have an outfit that hires people, and then their crowd is a controlled crowd that they use for their work, so they can vet the people that are working for them. So there are very many different scenarios. Some of them provide more of an advising service. If you want to do crowdsourcing, then they tell you how to use Mechanical Turk, how to use Crowdflower, and so on. Some of them build platforms. Some of them build the actual marketplaces where you do the work, like Mechanical Turk. So there's a wide spectrum of things. What do the companies do? There are all sorts of applications. For example, a company like Microsoft and Bing wants to know how well their search engine is doing. So they want to constantly be evaluating the relevance of their results. So they might ask the crowd, in some context, either wild crowd or people that they hire to do this, to evaluate how well the rankings are, the results relevant, or is the ordering correct for what they're showing, and they take the input from the crowd. Other companies want to offer products. For example, we know of a company that's trying to see if their price is competitive with the price of other companies. So they ask people, okay, here's this product, go and find it on the web and tell us what prices you find it at. And then they can match their price with what other companies are offering. Or we know people that in Haiti after the earthquake were trying to match, for example, photos of missing people with photos of survivors of the quake. But again, asking people to see if they can match them up to try to find the missing people. So there's a wide spectrum of applications. Companies are using this quite a bit. And that's why it's such an interesting area for us researchers to look at. So speaking of researchers, there's a lot of sort of academic projects. I've listed the icons from a number of universities that are doing research in crowdsourcing, Stanford included among all of those. Again, I'm probably missing a lot of universities. So that's basically the problem area. And now I'm going to be focusing on the research, and specifically some of the research that we're doing at Stanford. But before I get started in our research, let me just say a few words about crowdsourcing research. There's a lot of different aspects, like in my little cartoon that I have there, which is the blind men looking at the elephant, and everybody sees a different part of the elephant and thinks that they're looking at a different object. So crowdsourcing is the same thing. So there are many different aspects. For example, there are people that are interested in the human-computer interaction. What's the best way to present the problem to people, to get the input back from people? Very important problems in that aspect. Software systems. If I want to be issuing tasks like the one I was giving you, what type of software infrastructure can I use to issue the tasks, to collect the results, to keep statistics on the work, and so on. So there's a lot of computer systems work that's going on. On the human side, there's a lot of psychology issues, like how much reward do people need to do good work. If I pay 10 cents instead of 5 cents, will you become more accurate in my tasks, for example? That's more of a psychological question than a computer science question. Again, all very important parts of the puzzle. Machine learning people, there are many aspects to where machine learning can help in crowdsourcing, or you can use crowdsourcing to obtain training sets for your machine learning. It can go both ways with machine learning. And finally, information management, which is, I'm a database management person at heart, so that's sort of the aspect that I'm going to talk about. So let's focus on that aspect, but of course keep in mind that all the other aspects I mentioned are equally or more important than the data management side, but that's sort of my corner, so that's what I'm going to talk about today. And specifically, I'm going to focus on two aspects of the research in information management that we are pursuing at Stanford. One is looking at the crowd as a source of information. If I want to find a good restaurant in Cancun, or even in this hotel, they have so many good restaurants, I can ask you for the information, right? So you're a source of information, just like I have the web, I might have a traditional database, I have the crowd that can provide information. So the second part is I'm going to briefly tell you about one direction we're following. The other side is viewing the crowd as an information processor. That was my experiment that I did initially, asking you to analyze an image, give me an answer, for instance. So that's the first part of the work that I'm going to describe. So keep in mind that in both of these areas, as I describe our research and as you think of research in this area, there are at least 3 different dimensions of the challenges. And you can't get everything at once. So one of the issues is the accuracy of the results. We noticed that people wouldn't agree on the answers to my question, so you have to think about how accurate are the answers that are being produced by the crowd. There's also the cost. How much money am I going to pay people to do the work? And obviously there's a trade-off. The more people I pay or the more money I pay each person, maybe my accuracy will improve. There's also the third dimension, which is the latency. It takes time to set up a task depending on the marketplace that you're using. So you need to understand how to get the tasks out, how to collect the answers. And again, there's some trade-offs. If I go out in parallel and ask a lot of tasks, that's going to cost me money. More money, maybe it's going to improve my accuracy, but it's going to reduce my latency. If I do it one at a time, it might cost less. And I might still get the same accuracy after a lot of questions, but the response time is going to be much lower. So that's just a trade-off that you have to decide on. Okay? I think I'm just going to skip this. By the way, how am I doing on time? I didn't notice when we got started. How much? 20 minutes. Okay, perfect. Okay, so 20 minutes. Okay, so I'm going to talk about on the viewing people as processing sources, processing engines, for example. I'm going to talk about one very simple problem that we've been analyzing. Now, some of you might be puzzled why I picked such a simple problem. I mean, it's sort of a trivial problem, but you'll be surprised that even this simple problem has some interesting aspects to it, and I think it helps us understand the harder problems that you might be facing with crowdsourcing. So the problem I have is very simple. You have a set of images or items, and you want to apply a predicate like, are there more than 45 people in this image, for example? Or is this the image of a car? Or whatever question, a predicate. And then you want to just have a filtered data set where you've classified each object yes or no. So I'm just assuming a simple Boolean predicate, yes, no, as the output. And the predicate, however, is not a computer predicate. It's something that is going to be evaluated by the crowd, just like we did here. And I want to see here, I'm showing different responses. And as I hinted at, one obvious thing is to just use a majority, right? Say, okay, if the majority says yes, then it's yes. But if you think of it, there are a lot more choices that you could implement in just that simple decision of how do I decide when to stop, when to not ask more questions. So one of the insights that my graduate student, Aditya, had was to view the problem in the following way. Think of this space of scenarios, and the horizontal axis tells you how many people have answered no, in this case, to the questions. And the vertical axis tells you how many people have answered yes. Okay, so as you operate your decision for one item, you're going to move in this space, and your policy can be viewed as a set of colored dots on that space that tell you what to do in each situation. So the example I illustrate here, the green dots mean I haven't decided, so continue asking questions. The blue dots, this decision is pass. I call it pass to differentiate it from yes. So yes is what one person says. Pass is the decision that you make in the system as you're filtering the objects. Okay? So in this particular strategy, if you get, let's see, 4 yeses and either 0, 1, or 2, or 3 no's, you're still going to say yes. If you get 4 no's, so in other words, the first 4 votes you get in one direction or the other, you're going to say pass or fail based on that, and that's your strategy. Okay? So this is one example. I can actually get rid of the dots and just represent it as 2 curves. One blue curve that tells me where I'm going to say pass, and then one red curve where I'm going to say no, and the meeting point I call the decision point. That's sort of the point in the middle where you switch from yes to no. Now, this doesn't cover all the policies, but it covers all of the ones that sort of make sense. You could think of weird ones, but this sort of, it makes sense. But even this policies that could be described with these 2 curves, there are many different things you could do here. So for example, here is one where I say, well, instead of having the decision point at the corner, let me move it a little bit over. Why? Well, maybe because I know that it's more likely, I might not know something about the a priori distribution of my objects, and I might know that they're more failed, so maybe I will say fail more easily for example. So I might bias my result by moving that curve. Here is the majority one that I showed you earlier, that I described earlier, right? So the line is, I always stop at 4 questions, and then whichever has the majority of questions, that's the way I decide, right? So that's sort of the obvious simple one, but it's just one of many solutions. Here's another one where I say I'm going to wait until at least I have 2 more of one type than of the other, right? So I continue. At some point, I'm going to give up because I don't want to just spend infinite resources. So at some point, I'm just going to cut it off and I have to make a decision. Okay, so that's another strategy that might be good. I'll just continue asking questions until I get 2 in favor in one direction or the other, or I run out of money and then I have to stop and decide one way or the other. Okay, so many different choices. And furthermore, there are some interesting questions. Look at this policy that I showed you there. This one, I mean, it's okay, but you can very quickly see that it doesn't really make sense because once I've gotten into this region over here, it's all going to be red anyway. So why am I asking questions up here? I think I have a point. Do I have a pointer here? Yeah. Why am I asking questions here if I know I'm going to say fail anyway? So I'm just wasting my money and people's time. So I can replace that by that policy. So you can already see that there's sort of like an algebra of shapes. You have these shapes, and some shapes dominate other shapes in terms that they're always better than the other. So there's a lot of interesting things you can do there. Then, of course, you want to decide of the shapes that make sense, which one is better. So suppose I show you those 2 shapes. Which one should you use in your system? Well, now we need to evaluate both of them. Both of those make sense. And we've come up, I'm not going to bore you with all the details, but I'm just going to describe briefly, there's a methodical way of evaluating how expensive a strategy is, the expected cost on the average, how many dollars am I going to spend to answer questions, and also the expected error. Over all possible scenarios, what's the quality of the results that I'm going to get? So then you can compare your strategies and ask questions like, I want to find the one that minimizes the expected cost, but giving me some guaranteed level of correctness of the answers. Or many other sort of optimization questions that you can ask. Okay? So that was just the motivation for the work we've done. There's a lot of additional details you can read in we have a SIGMOD paper that goes into a lot of detail here. But let me move on and just talk about some of the, I'll skip this. There's a lot of extensions. Again, as I said earlier, I started with a very simple problem just to sort of motivate the issues. You can think, for example, I mentioned one of the extensions, probabilistic strategies. The strategies I described there are deterministic. I had blue and red dots that you always did the same thing when you got to that point in the grid. But you could have a probabilistic strategy where you get there, you flip a coin. With 90% probability, I'll say pass. With 10% probability, I'll continue asking questions, for example. It turns out, very surprising, that the probabilistic strategies are better. You can find strategies that are better than the deterministic ones. So if you want the best performance for the lowest cost, you should use a probabilistic strategy, for example. That's something that I hadn't thought of when we started doing this work. Okay? Then, in addition, there are different types of algorithms that we've been studying. I sort of show you the simplest type of algorithm you can think of. But there are other algorithms like finding the max, the best image of a group of images, sorting things using the crowd, doing entity resolution, for example, trying to find out what object matches other objects, using people to help you, to guide you, and so on. So we're exploring a number of different algorithms for this. Okay. Let me stop here. I know, ask questions. I mean, I like questions. So if people have any questions at this point, because now I'm going to switch to just like 5 minutes, if I still have time. Yeah, 10 minutes. Okay, so I'm going to switch topics. But if people have questions or comments about this, I'll be happy to take them. Yes?
But you're assuming that all the individuals have the same information. I mean, there might be individuals that are much more knowledgeable about the subject than others.
Absolutely, yes.
So, I mean, are you a Republican or something?
A great point. Yes, that was the simple model where, yes, each worker was independent of the other workers in that model. But the slide I had skipped tells us some of the extensions we're looking at, right? So what happens when workers have different abilities, for instance? Or how do I track, as I said earlier in my experiment, you want to keep track of who's a good worker and who's a bad worker. How do I do that effectively? And what's the accuracy of those estimates? If I say you're a bad worker, how confident am I that you're a bad worker? And what's the strategy? Do I fire you? Do I give an incentive? Do I pay more to the workers that did better? There's a lot of interesting questions. So my simple, the analysis of the simple strategy was just to sort of whet your appetite and get you interested. There's lots of extensions that are needed and we're working on and a lot of people are working on. There's other things here that you can see as current topics. Okay, any other questions? Okay. Well, we might have a few minutes at the end. So let me move on, just tell you about the other side of the research that we're doing. This will be even briefer. Remember, the idea now here is that we're going to view the crowd as sources of information. So what we'd like to do, our vision, since we're database people, is to build a database that can go to traditional databases or the web or to people as necessary. So we'd like to build a database system that's smart enough to know where to go and get the stuff it needs. But the characteristics of this data source is very different than from this source and from this source. So the techniques have to be different. So here is our vision for this database system. It's going to have a conceptual schema that the users are going to see, an actual schema that's the materialized view if you want, and then you have the system underneath. So let me illustrate just with one example how the system works, just again to give you the flavor and the idea of what we're building. We actually have a prototype and if there's experimental results for it and so on. But let's take the example I mentioned earlier. You want to find restaurants that are good. So this is the view that the users have. So this is what we'd like to provide the users of the system, a view that they have restaurants and ratings and the type of food that those restaurants serve. So the user does not know about the crowd or where the data is, they just have that view. But underneath, we're going to divide that data into segments depending on how we get the data. So we have the anchor column, which is the sort of the keys of the records. Think of them that way. It can be generalized, but just think of them as keys. And then the other tables are built that way because we're providing what we call fetch rules. These are rules for going to a crowdsourcing source and getting information. So for example, this fetch rule is saying that you can go and ask a person, tell them a restaurant name, and they will tell you what they serve at that restaurant. Okay, so that tells us what is the functionality of the people that you have. Now, you can actually have multiple fetch rules per segment here. You can also, in this example, say, I could go and ask people, French restaurant, what are French restaurants that you know of? So depending on your application, you can go either way. So you can have multiple fetch rules for each of these segments. Then these blue segments are what's materialized. These are the answers that you are getting from users as you go and get the data from the crowd. You also need some way to resolve them because you know, for example, the view up there, you have to combine the attributes here into one number. So for example, the Japanese California restaurant has 4.9 and that we need to average these numbers to generate that value, right? So in addition to the fetch rules, we're telling the system how to cleanse the data in database terminology. Okay? So those are the key components. And then the logical view, again, is like you collect data from the crowd here in these tables, you fetch, then you resolve, and then you join the tables and create what the user wants. But what the system needs to do is just the opposite, right? Because it's not going to do any of this until it has a query. So it's just like materialized views, like querying views. So the query will come in, you'll tell me, oh, get me French restaurants that have this rating, and the system will say at runtime, oh, I might already have some in my database, but if not, I'm going to go ask people for their opinion of restaurants. So dynamically, the system is going to decide where to get the data and ask people, cleanse the data, and will stop when it has enough answers for you. So that's sort of the vision that we and other universities are following for this sort of crowd database system. Okay. There are obviously a lot of interesting challenges here for those of you who do databases. There's query optimization is one of the hardest aspects of traditional databases. Here, it becomes harder because you have new operators, like a fetch operator, resolve operator. So your query optimizer now has to deal with how do I order these operators. We have to deal with extensions to the query language. So for example, you notice in the query there's this at least 8, because since the crowd is infinite, there's no limit to how many restaurant names we're going to get from the crowd. So you have to give some guidance. I want at least 8 French restaurants with a rating of 4. So then that drives the system to ask questions until it has enough data to satisfy the query. So that also has to be introduced into the query plan, and the query optimizer has to understand all the complexities of dealing with people and at the same time the traditional data sources. Okay? We have a prototype. I'm not going to go into the experimental results, but there are all sorts of interesting observations that we have even with our preliminary system, showing, for example, how this little graph just tries to show that depending on the type of fetch rules you have, sometimes your questions, if you don't have enough power in what you can ask people, then the question can end up taking a long time. This shows how long you have to run to get these number of tuples. This is a real live experiment on Mechanical Turk where we're collecting data from people. If you have people that are more powerful, that can do better types of queries, then these are the different colored scenarios with different query optimization strategies, and you can see that they provide different results. Basically, this graph here is just to show you that there are results. You can read in our paper if you are interested. Okay, so to conclude, and maybe we have a little bit of time for questions, I think crowdsourcing is an exciting new area. There is a lot of interest from small companies right now. Honestly, I don't know if it's going to be a huge commercial success in the future, but that's not really what's driving us. It's just there's lots of very interesting questions, and there's potential to provide the end users, whether they're corporations like Microsoft or yourselves, with higher quality, more diverse data than we can get from today's computer systems. So.
Muchas gracias, Héctor.
So,
tenemos tiempo para preguntas. Así
so
que,
we have a little bit of time for questions.
Sí.
So maybe we can have the lights up so I can see who's asking the question.
¿Alguna pregunta?
Yes, over here. You can ask in Spanish or in English, and I'll translate, or I'll try to translate.
One of the big challenges I imagine here is the response time of the system, right? Because
exactly.
You're used to have your response like in a couple of, I don't know, milliseconds with a traditional database system, whereas here you might need to wait a couple of minutes.
Or days, maybe.
Right, exactly. So how to deal with that? For instance, the user could say, give me whatever answers you have in 1 minute. I don't want to wait for longer than that, or how do you cope with the time issue?
It's wide open. I mean, anything is possible, yes. Now, in some scenarios, I think it'll be fine to wait a few days. So these queries are going to be more like analysis questions, right? So you are in the company and want to know who in the company might have these abilities to help me in this project. Right? It's the type of thing you would traditionally do by asking your friends, and it would take days to find out. So if you're going to the crowd, which in a company scenario would be your employees or the people that are participating in the company's Facebook, then it's okay. It takes a couple of days. It's faster than it would have taken you by doing it manually yourself. Yeah. In other scenarios, maybe you want faster response time, and then maybe this type of system will not be appropriate for that. But whatever your scenario, there are still interesting challenges. How can we speed up the execution? For example, in the database context that I showed you there, if I have multiple fetch rules, right, then I showed you in that graph I went over quickly that depending on which fetch rule I utilize, I can get the answers faster than in other cases, right? So if somebody wants, say, Chinese restaurants, then should I first ask the users, okay, give me the names of Chinese restaurants, or should I ask them, here's a restaurant, is it Chinese? The response time is different. How do I decide which one will give me the fastest response for my query? Hard problem. I don't know the answer, but that's a great research area, I think. Yes, back there? Yes, please. Oh, sorry, you have the microphone here. Sorry. You got beaten.
Gracias, voy a hablar en español. Me llama la atención la similitud que tienen, cómo están estructurando el modelo el esquema de datos es muy similar a lo que se utiliza lo que se utiliza en el tema de RDF en triples cuando separas tu metadata en la persistencia de datos. ¿Han pensado en utilizar una base de datos no relacional, una base de datos semántica para almacenar esta información, que creo que podría ser una forma más eficiente de hacer esas búsquedas y consultas?
Okay, so the question was, why did we go with a vanilla relational model? Why not RDF or XML or whatever you like? And yes, we thought about it. Actually, our group has done work in semi-structured data in the past. We just felt that it was hard enough with relational that we didn't want to throw too many things into the problem yet. So it was easier to just use the traditional database relational model. It's not that we don't like the others. Yes, it might be very natural, but we had our hands full with this. That's the main motivation.
Yes, I was wondering the relation of this kind of data gathering in comparison with the actual polls.
Polls.
Polls. So,
Yeah.
For instance, if I want to know who's going to vote for whatever party in Mexico,
Yes, yeah.
could I use something like this? And how do you deal with the interest of the participants? How, and surely in other subjects as well. I mean, the bias of the interest of the participants is important. So how do you deal with that?
Yes, great questions. As you're beginning to see, I mean, I don't have the answers to all these very good questions because this is, I think it's a new topic and we're just sort of getting started. That's very good. I hadn't thought of that aspect of sort of using it as a polling system, but in principle it could be, right, because that's what polling agencies do. That somebody comes and says, we want to get this type of information, and they form a poll and they go out and do it. So why not sort of automate the process? You define your schema, you define the fetch rules, and then on the fly you could do like mini polls. You could just, here's what I want to know, and then you could call people and give them resolution rules for how to combine the results. I think it's a great example. How to deal with biases, another great question. I don't know, but I guess your resolution rules would have to take that into account, right? In our system, I'm just making this up as I'm going along. Your resolution rule is fairly, it can be any program. So you can just code something up that says, okay, look at their party affiliation, look what they said, and somehow weigh their vote by their party affiliation or something. So you could do something like that. But I love it. It's a great example. Do we have, Jaime, do we have time for questions?
Hi.
One more.
Also in relation with these people as processors,
yes.
What do you think is the importance? Is there any of the topology of the social network and each people's or each person's position in it?
Sorry, can you repeat? So
you know, with people as processors, do you consider it important their position in the social network that they form, and the topology of the network itself?
Okay, another good question. So the question was, what about the social network? In the filtering example that I showed you, there was no social network, right? Each worker was independent. But actually, there's a company that came by to talk to us that's in the Bay Area that was doing crowdsourcing on LinkedIn and taking into account the social structure. So the idea is that you wanted to rate LinkedIn profiles to see who was better suited for a job. But their idea was that, which is I think what you're saying, is that if you're asking two people to compare two LinkedIn profiles, if you're somehow associated, you know those people, then you're a better person to judge if who's better, for example, for the task. So they were looking at using the social structure to sort of give tasks to the appropriate people who might provide better input. So it's definitely an important direction. We haven't studied it ourselves in our research, and maybe later on I'll remember the name of the company and I can give it to you if you want to get in touch with them, but right now I'm blanking out on the name of the company. Okay, so I think that's it.
Muchas gracias, Héctor.
Thank you very much. Gracias.